Okay. Hello, everyone. Welcome to the neural computing lecture. So, you can hear me, yeah? That's the usual checks. Right. Thank you for that confirmation. Just a moment, let me get things set up. Meanwhile, please take your attendance. Yeah, please take your attendance. The QR code is on Spectrum. I've also uploaded the slides for today. So this week we'll be doing automatic differentiation. All right. Just here. So you can see my screen, yeah?
Yes.
Thank you very much.
Yes.
So this week we'll be doing automatic differentiation, right? Just to recap, now last week what we did was backpropagation. We did. Yep. Last time we did backpropagation, where okay, so we did backpropagation, right? And we've recapped how the forward pass in order to do backpropagation. Yeah, remember that we have the neurons here, the single layer perceptron. I give an example, for example, yeah. And then the usual stuff. Then what we do is we draw the computation. No, let's not do this. How should I say this? Okay, last week we did backpropagation, and we know that given a function, right? We draw computational graph. We did the computational graph, and then we did the forward pass, and also the backward pass. This is to recap what we did last week. Forward pass and the backward pass. Now, So this is, the notes from last week. We have a forward pass, and then using the where we compute the local gradient as we go along, right? As we go along, and then we did the backward pass, right? We assume the gradient coming in is 1, and when we compute the backward pass, we also compute, we utilize the local gradient that we've computed in the forward pass, right? And both forward and backward pass uses the chain rule, uses chain rule here. So just be careful on that. But the idea is that in for neural network as well, we can do the same thing. So here we have a computational graph. This is not a neural network, right? Because neural network have weights and you have biases, you have activation functions and all that. But this is just a simple computational graph, right? X plus y, x times y, and things like that, right? So x plus y, and then times z, yeah? So this is a computation graph. But we find that if we compute the local gradient going forward, then we do not have to do that computation going backwards, right? So we can make use of the local gradient. So that's the main idea here, right? Now, today we'll be doing automatic differentiation. Now, what is automatic differentiation? Basically, automatic differentiation is how, in essence, yeah, today's topic is about how to actually do backpropagation, BP, here, in code or in computer, right? How do we actually do that? Right? Because in the backpropagation that we've done this, so as you can see, we have a function, and then you can because we are doing on a piece of paper, or well, on the Jamboard, basically we're using it manually, computing all the local gradient. We can calculate for the chain rules, right? And we can also derive the gradient of the knowing the function x plus y. We know what is the dq of the x is and what is dq of the y is, and how do we translate that into computer, right? Or how do we do that? How do we do that into code or into Python? So that's the idea for automatic differentiation, our lecture for today. So this is automatic differentiation. So we have the multi-layered ceptron, right? And we have the error that we want to minimize. Again, we need to compute the gradient with respect to the weights, minimize the error by forward propagation of derivatives, and then back propagation and update the weights as such. This is a problem. How do we actually do this? How do we do this, right? Especially when the network is getting larger and larger and larger, right? It's quite tricky. Now, if we can do this in a computer program by, for example, yeah, we can do analytically, right? So you can use, for example, solve. You have a function, and then you solve using symbolic expression, SymPy, right? But if we solve this using symbolic expression, we can't differentiate algorithms this way. Or we can solve numerically using finite differences. Now, where have we seen this? This is actually where it's in the slides I think in the first slides, I think, when you are there is a slide talking about finite differences. But of course, if you have finite differences, you have errors, right? And errors, as you probably know by now, that numerical errors, when they accumulate, right, your approximation or your calculation will, quite will be running off from the true values that you're looking for. How do we actually compute the gradient then? So we are, like I said before, we are using local gradient information that we catch, right, along the way when we did the forward pass. But then again, how do you do this in coding, right? This is the this is the crux of the lecture for today. So again, automatic differentiation is a method, right, to get exact derivatives efficiently. Take codes that compute a function and use that to compute the derivative of that function. So the idea is this is the idea. Whenever you compute a function, you also compute the derivative of that function instantly somehow, right? That's the idea. So you have a function, right? X equals f of t, for example, of f of x or t, right? Whatever f of t, right? Something like that. And then when you compute this function, right? For example, okay, we'll just do I don't know, 2t, yeah, just 2t, right? So we can compute this, right? If, for example, t equals 1, right? So this is x equals 2, right? And then at the same time, we also construct the local gradient, right? Just 2, right? And then, okay, 2t is not a good example here, so it's just, we'll take a t squared. Yeah, that will be 3. And then you have dx over dt, there will be 2t. So t equals 1, x equals 1, dx dt equals 2, right? So as you compute the values of the original function or the function itself, you also compute the values for the gradient. So you do not have to, you do not have to wait until you reach at the end of the network and then you have to calculate the gradient back. No, you compute it instantly. So that's kind of the idea of automatic differentiation as well. Okay, so the goal is to write a program that efficiently computes the derivatives. So this is the goal here. This is the goal here. Now, there'll be some exercise afterwards, yeah, some exercise afterwards that you can do, right? So hopefully today's lecture is not too sleepy, hopefully, yeah, by having these exercises. So before we do that, we have to consider the problem. Let's say this problem, we have something of a function x and y, and a equals xy, and b equals to the sine of x, and z is a plus b. How do we, what does the computational graph looks like? So I'm just going to draw it here. X equals, I don't know, right? Y equals something as well. B is a sine of x, and a is the multiplication of x times y, right? And z is a plus b, right? So x, y are functions of some variable t. This is our assumption. Yeah? This is our assumption. So x equals, actually x is equals x of t, and y is equal y of t. So we can think of it this way. We don't know what x. We don't know what is x. We don't know what is x. Right? We're assuming that x is some functions of some variable t. Right? So the computational graph I think you can do the computational graph by now, right? So this is sine of x, and just do sine here, right? Because usually it's the operation is inside the circle, right? So just do b equals to sine of x, right? And then you have y here, and then which is the multiplication here, right? So this is a equals x y, and then you have uh, the addition here, right? Which is z equals a plus b, right? Now we know that this is our assumptions. Yeah? Assume, right? X are functions of some variable t. Now we want to um, take the derivatives, right? So since we have x, y, b, a, and z, so we'll take the derivatives dx of dt, which we don't know, right? Because we don't know what the function is, right? We're just assuming it's a function of some variable t. It can be x equals, again, it can be x equals t squared or x equals 2t, whatever, right? We don't know. We just assume that this is a function of some variable t, like a placeholder, lah, right? And then you have dy of dt equals, I don't know as well, right? And then you can do d, write that properly, db of dt, which is equal cosine of x dx dt. And you can also have dA of dt equals x dx over dt plus y times dy over dt. Not dy over dt, dy of dt lah, because it's not the fractions. And then you have dz of dt equals dA of dt plus dB of dt. So this is what in our forward pass that we want to compute, right? Now we want to compute. This expression is not complete yet, right? It's not complete yet. But before I go into this expression, right? I'll just show you. So these are from the slides, yeah? These are also from the slides. It's also in the slides, right? Consider problem below, right? We've done the computational graph. So this is how you do the problem in Python, right? This is the computing the just the functions lah. This is straightforward. X equals 1 or y is equals 1.5, and then you can have your values for each of the functions, right? But let's just the idea is to differentiate the birth problem with respect to some variable t, right? Now z is a function that is dependent on y is a function that is dependent on x, right? To differentiate z, we use the chain rule, right? Of course, this can be generalized, right? We only have a very short computation graph at this point, so we don't have a very long function here, right? Right, we've done this, right? Now, before I go into this, let's do some maths. Let's do some maths here. Now, we have just some notes. on the derivative. Derivatives here. We have b equals to sine of x, where x is some function of t, right? Why is it that b db dt, right, is equals to cosine x dx dt? What rules are we using here? So here, I want you to think of differentiation rules, right? So right. So I want you to think of differentiation rules. Why is it dB of dt equals to cosine of x and dx of dt, right? So we know that from using the chain rule, right? Using the chain rule, what does the chain rule says, right? Using chain rule, let me just go down. So, you can just Google differentiation rules images, and, you get all sorts of rules here. So this is the rule. So the chain rule is very convenient when you have functions of a function of functions, right? Which is what we have for our neural network and for our computational graph. You have a function f, which is a function of g, but g is also a function of x. So you can use the chain rule, right? So in our case, we have b, which is a function of x, but x is a function of t. So we want to uh, differentiate b with respect to t, right? And then you use the chain rule, which basically, this is just a chain rule. You already know this, but I'll just, then gx. This is just, I'm writing it again. The differentiation rules that you've seen just now, right? So that being saying, if b is equals sine of x, where x is, a function of t, right? Then dB dt is dB dx times dx dt, right? Which is equals to dB. So you differentiate this with respect to x, which is cosine x, and then you have the dx dt term over here, right? So just my point is, I want you to be comfortable with the differentiation rules, because in this course or in this subject, or as a deep learning as a whole, if you're not comfortable with the differentiation rules, from you find it weird or something, then it's kind of a miss the whole point of deep learning, right? I understand you don't need this, right, to actually build models, but this, gives you a deeper understanding, because we are doing deep learning. Why not deep learning the deep learning itself? So that's kind of the idea, right? So now you know the differentiation rules. How about the next one? A equals xy. X is some functions of t. Y is also some functions of t. Right? Why is it dA of dt equals x dx of dt plus y dy of dt. What what you know, what rules are we using here? Yeah, so I'll just give a question. What differentiation, or which differentiation rules, because we have many, which differentiation rules do we use here? Differentiation rules do we use here?
Is it the product rule?
Yes, it's a product rule. Thank you very much.
But
So
doctor,
you have,
if it's the product rule, then it should be x dy dt plus y dx dt, right?
plus
Y dx dt.
sorry. Yeah, that's true. You're right. You're right. Yes, you're right. You're right. Okay. We just thank you very much for that. Did I make a mistake in the slides? Just a minute. Yeah, sure. Yes, I think this is x dy dt and y dx dt. Okay. So here you are using the product rule. You want to use the product rule, right? So what is the product rule? Given that you have some uv, right, where u is u of x, v is v of x, and then you have u dv of dx plus v of du of dx, right? And therefore, please be conscious of the rules that you are using. The chain rule. Why am I stressing this out? Because when applying the automatic differentiation, you actually have to know these rules, right? In order for you to code it, right? So you have to know this, because what we're doing is, in automatic differentiation, is we're translating this into Python. We're translating this into Python. We're not using any functions. We're just translating all of these derivatives into some primitive or native form of Python. Yeah, just doing some divisions or multiplications, right? So that is so be careful with that. Yeah, just be careful with that. Now, how about okay, I'll just go for this one. That's the last one. The last one. Z is equals a plus b. Which rule is being used here? It may look simple, I know it looks simple, it looks straightforward, but I just want you to be aware of which rules are being used here.
This is the sum rule.
Yes. So here you are using the sum rule, right? Using the sum rule, where d of x or d of d, yeah, You have two functions, which is a function of x. Then you no. And then just take this, right? So dz of dt equals dA of dt, dA dt plus dB dt. Now, dA dt and dB dt has been, had been solved earlier, right? So you know that. So this is x dy dt plus y dx dt, right? And then plus cosine of x dx dt. So it's kind of long. So this is kind of this term, and this goes for this term. Yeah, simple as that. So thank you very much for your participation. So please be aware of the rules here, because in deriving the gradients with respect to width, you also have to differentiate, right? And in order for you to find to differentiate and to find the derivatives and to find the gradients, you need to know the differentiation rules, right? You need to know the differentiation rules. Okay, now we have this. So we have we've done the difference. We have the functions. We have a function here. This is how you do it in normal Python for the normal functions, and then you differentiate the functions, right? You find the derivatives of each term of each variable here, assuming that x and y is a function of t, some variable t, and this is how you do in Python, right? Now you can code if dx, you have some if it's the values of dx of dt and dy of dt, then you know that using the the rules that we've done before, you know that dA of dt, so the x times dy plus y times dx. And so for dB is just take the cosine x times dx, and dz is just, we just add these two up, right? Just add these two up, right? So in maths, now here is the trick that we're using in Python, right? Just now we say x is a function of t, y is a function of t, right? Now we are saying assume that t is x, right? So x is equals x, right? Y is equal x. Oh, sorry. So we set t equals to x, right? And then we find the derivatives. So when we do that, the derivatives of x with respect to x is 1. In Python, we set this as 1. And this becomes 0, right? And then the rest is the same. This term does not change. This term also does not change, right? If we change dx to 0 and dy to 1, then we'll get the final one. We will get the dz of dy. So if by doing, we are assigning t equals to x, we'll get dz of dx. This is our somehow objective here. This is forward computation, right? If we forward, we are computing the gradient with respect to the variable x. The gradient or derivatives of z with respect to variable x. How do you do that? Is by seeding dx equals 1, dy is equals 0, then the rest just follows, right? The rest of the code just follows. And so if you do it the other way around, you'll get dz of dy, right? So this is forward mode auto differentiation in a sense, yeah? In a sense. We only need to seed this code. We're calling this seeding, yeah? We only need to seed the algorithm with the variables that we are interested in. Okay, so to compute dz dx, right? The derivatives of z with respect to x. So we need partial derivatives. You just need to seed dx equals 1 and dy equals 0, and so forth. Similarly, seeding the other way around, you compute the derivatives of z with respect to y, right? Or the partial derivative of z with respect to y, right? I'll just pause for a while. Can you follow up till now? Is this fine, or is there some questions, or something that you kind of confusing?
Is there a reason for us to like t equals to x, or is it just for simplicity's sake?
This is for why are we doing this? Is for how to compute. This is how should I say this? Is there a reason t equals to x? Is because we want to seed the algorithm, meaning that we want to do this, right? We want to do this calculation, right? At the end of the day, we want to find this, dz of dx, right? But how do we do this in coding, right? For the forward computation, because the back propagation, we are not going to do this. There's some other clever ways, but in order to do that, you have to set dx equals 1 and the rest of the variables equals 0. And then you'll get these partial derivatives. So let me just have a look. Let me just a moment, yeah, just a moment.
Can I ask a question?
Yes.
In the code and also in the math, I see that you have x and y, not the partial derivative, just the x and y, and we don't have any values for that. How are you calculating that?
Um, we don't have any values for x and y,
X and y
right? Yeah.
in the
Yes.
third line.
The third line, this one, right?
Yes, sir.
We I'll be showing later. We'll be using a concept using a dual number, right? We'll be using a concept called a dual number, where you have the values of the variables and the gradient. So in here, you don't have the values of x yet, but where is it? Yeah, here, because the functions, this code has to be seeded in a way by this code, right? So you have x and y, a, b, and z here. So you have to seed these two values as well. I'll show that later. So this is this dual number concept is somehow, I think, students are a bit confused. I find students are a bit confused. Okay, I myself can be confused as well, right? It's kind of challenging. So going back to the slides, right? So you might see that, okay, why are we, again, it seems like, very strange and funny, right? To have x not, it doesn't have any values here, or it doesn't have any expression or equation here, right? We just know that x is a function of variable t, right? And it's also funny and strange when you have dx of dt, we don't know what dx of dt is, right? But the idea is actually to set t as x or to set t as y so that we can choose what do we want to differentiate the final variable z with respect to? So if we want to find dz of dx, then we'll just set this as tsx and dx as 1. If we want to find dz of dy, the partial derivative of dz with respect to y, then we'll just do it the other way, right? Then we'll say t equals to y, and then this becomes 0, and this becomes 1. That is kind of the whole idea. So if we go back here, what is the computation functions? I'll draw this again. Yeah, I'll draw this again. Maybe I'll do this. So you have sine here. So b equals sine of x, right? Because in Python, at the end of the day, you have to, even we have x equals to t, you need to, at the start of your program, right? You need to actually give some values to your variables. For example, x equals to t or whatever there is, right? Then you need to t equals 1 or t equals 0 or t equals 0 or something, or 0.1, whatever, pi or something, right? You need to give some values to it because it doesn't understand, in Python, it doesn't understand symbols. Okay? Unless you're using, of course, you're using symbolic pi, right? Sim pi, right? Then the story is different. But if we are using symbolic expressions, then there's some other problems that will be coming in, right? So we want to do, the idea is to do the computation very clean and simple, and it kinds of builds up on top of one another. You'll see what I mean after we actually finish the whole of automatic differentiation. Hopefully, yeah, hopefully. All right, so we'll do this, and then we'll do this, right? And then we have some c equals a plus b, and then you can do db over dx here, and you have dA over dx here, and you have dA of dy here. This is a equals x times y, and then you have dz of dA over here, and you have dz of dB over here, right? And you have dz of dt, which is dA of dt plus dB of dt, right? Now, just a moment, yeah, just a minute. Give me a few minutes. I think I need to show this. So we've done this. Let me see if I can demonstrate it. Just give me a while. Okay, I think can do this. So if we switch. Okay, so before this, do this. Some demo. So example here, x equals 0.5. That's the same. But no, we don't have any values, for example. Y equals something. And you have b equals to math. Of x equals x times b, and then c equals a plus b, and then just going to do print. Never mind. This is the normal functions, right? Done this. You have dx, dy, and then you have dA equals x times dy plus y times dx. Math cosine of x dx, dz equals dA plus dB. This is going to do print sec d of dx dz here. Here, of course, so how do we compute this? So the idea is we want to do this computation, right? We want to do this computation. Now assume we know the values of x and y. I'm just going to use the same values that I use in the slides. I think I've used this in the slides, 0.5 and 4.2, right? Now we want to know what is dz of the x. And you just set this as 1, and you just set this 0. This is the, by the way, this is we'll be doing some, oh, I bet dA, dz, this is dz plus dB. Right. So by the way, this we'll be doing some exercise for the forward mode automatic differentiation. I think we have ample time to do it. Okay. So this is the idea. You have some values over here, some known values. And the idea is if you want to solve for dz over dx, right? Because you already know this is the, what was this, I guess? This is the, what rules is it? And this is the chain rule. It's the summation rule and the product rule. This is the product rule. Differentiation rules, right? It will automatically calculate the, it will also compute the dz of dx. So that's the idea that you get with this. Okay, so this is the idea that we're trying to push for. Okay, now so if we see dx dy equals 1 and x equals 0, you just need to print if we want dz of dy, then we'll just change this from 0 and this to 1, and you get dz of dy. Okay, so that's the idea. Now, what is the problem with this? What is the problem with this? Is that if you have a lot of variables, right? A lot of variables. For example, you have x, y. Maybe you have, I don't know, m equals something, n, and I'll just do numbers lah. X, maybe x1, right? x2, x3, and blah 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 x1000, right? 1000, blah 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 blah, and then it's the same goes with y. When you have this, right, and every time that you write your code, dx1, dx2, dx3, x1000, right? So you have to see, for example, you want to find, for example, find dz over dx3, right? So you have to set the others as zeros. And the variables that you wish to differentiate with respect to as 1. Not this one, this one, dx over d3. dz with respect to dx3, right? And here is 0 again, right? So assume that, you have dx4, blah, 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 and dx4 here, blah, blah, until dx1000. We have 1000 variables of x's. Okay? So you have to set all the others as zeros, and you're setting the one that you are interested in. This is what you're interested in. Okay, and that is just computationally very inefficient. This is very inefficient. Okay, so this is very inefficient. I'll talk about this in the slides again. So as you can see, we've successfully computed the gradients for a specific function, right? The process was not exactly automatic, right? We still need to analytically apply differentiation rules and then write into the code, like you see just now. Now, what we want to do is we need to formalize a set of rules, right? Where we have actually discovered 3 of these rules. Well, not really discovered lah, which mean we have translated 3 of these differentiation rules in math to Python, right? So if C equals A plus B, then DC equals DA plus DB. And if C equals A times B, then DC equals, using the product rule. This is how we translated this into Python just now. And if C equals sine of A, then DC equals to cosine of A times DA, right? And are we restricted to these rules? No, we have, because if you look at differentiation rules, there are lots of, even this, right? So derivatives rules, right? You have I hope you can see this. It's a bit small here. It's exponential functions, derivative rules for exponential functions, log functions, trigo functions, inverse trigo functions, hyperbolic, inverse hyperbolic. Well, of course, you have the basic derivative rules here, right? But you also have different rules for a lot of different rules. So the idea here is that you need to formalize this rule, right? You need to formalize these rules and translate it into your code. Translate it into your code here. So instead of sum rule, you also have addition, and subtraction, and division, and so forth, right? And all the different differentiation rules to cover the different cases or different situations that we need to handle, right? So we need to formalize the rules. We only use 3 of these rules because our computational graph is very simple, right? So to translate using the rules, we simply replace each primitive operation by its differential analog. And of course, the order of the computation remains unchanged, right? If a statement is evaluated with another statement, then the differential analog is also evaluated before the analog statement else. So what this means is, I'll just delete this here, so because you already know what I mean. So this I'll just do this, and so if here it goes from x, y, b, a, and z, right? So your differentiation must also follows the same, of course, order, right? Dx must be evaluated dy, and then the a, although x and y here are independent, yeah, only b, a, and z are, the downstream of the computation graph. So, but in that sense, you have to do this. Of course, you can't do, you can't do, not you can't do, in the way you can, but the order of the computation remains unchanged. Bz has to be at the end. Bz, this has to be at the end. Of course, you can do this, I think, because this just depends on the previous one, these two, right? Just for consistency's sake, we'll do this. Yeah, we'll do this. So you want to, have a try in your collab or notebook. It's fine, right? So this is forward mode automatic differentiation, right? This is forward mode automatic differentiation. I'll just pause for a while. Do you have any questions? If you have any questions regarding the assignment, as you can leave the comments in the chat as well, yeah, right?
So sorry, Doctor.
Yeah.
May I ask, what's the difference between the symbol of differentiation that you use in the slide? Sorry, Doctor, can you go back to previous slide where got the differentiation part? The previous, yeah, this one. Why you use this symbol, but the previous one you use the letter D? Yep.
Okay, so it's my bad. I'm I'm inconsistent here. So where? Sorry, yeah, this is
It
my
is
bad.
okay, it's okay.
Uh, is because we are these symbols, right? This is partial derivatives, right? So it's more, how should I say, appropriate notation, I guess. Just a moment, yeah. So, but you don't have to you know uh, crack your head. Just some inconsistency of the symbol. It means the same thing, but it has a slight difference. Yeah, let me find the difference. What is the difference? Can I The difference? So it's how you is the difference between how you write partial derivatives and how you write just normal differentiation. Look up this. So if you have normal derivatives, right? So just if I bring it over here, this is from Wiki lah. So you write this way, right? dy over dx, dy over dx, dy dx, and df dx, right? Or this notation. So this Leibniz notation. And if you have partial derivatives, then you have these curly symbols here. when do you have partial derivatives? When your function is a function of more than one variables, then you have to have partial derivatives. My bad for that. Maybe I'll try to change that in slides. Yeah. So this should be D, I guess, instead of the curly. So so if you Google partial derivatives and derivatives, is a notation, just a different notation. So if you're for normal derivatives using the Leibniz notation, not normal, I mean the main notation for derivatives is this dy over dx. But if we are specifically talking about partial derivatives, right? Partial derivatives f will equals to x, then we are using the curly d's.
All right. Thank you.
Right. Thank you. Thank you for that. Probably I'll fix the slide to be more consistent. If you do have any questions about the assignments, also you can just leave the comments in the chat. Probably address the questions, maybe not during the class, maybe a little bit after the class. Yeah. Okay. So this is forward mode automatic differentiation, right? Now, as you can see in our this one, we have we are computing dz of dy, right? But what we want to do is we want to have like one variable x, which actually stores the values of the value of x, and also the derivatives of x. This is what we want to do. We want to have a x, right? We want to kind of declare this variable, and it stores two values. One is the value of itself, yes, x equals 0.5, and the derivative values of itself, which is in this case it might be 1, it might be 0.5, it might be I don't know, right? We can assume this to be anything at this point. Yeah, this would be confusing to you, but I'm hope you can be a little bit patient, that after we've done the back propagation, the reverse mode, because we have forward mode here, forward AD, we also have the reverse AD, which is the back propagation. And once we've done that, you can see that the whole story comes in, and you can see the whole point of why we're setting as 1 and zeros, and so forth. And why are we assigning some random numbers here? It looks like, oh, if it's here 0.5, why is dx 1, right? You might ask me that, right? So the idea now is that we want to have a variable or some way of storing the value of x and its derivative, right? We want to do that because in this way we can't keep track, right? We can't keep in this way. We can't keep track. We have to look at each of the variables. So x stores its own values, and dx stores the derivatives of x, and then you have you want to halve the variables that you use, the number of variables that you use, right? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 variables. You want to kind of like it seems like effectively you have like 5 variables out of it, right? So what we're going to do is we use the concept called dual numbers, right? This is the old way, right? In order to do forward automatic differentiation, we need to store both values of the variables and the local gradient, right? This way we only need to keep track of one variable, but you get both information at the same time. So we can use the this is the old way, but we can also use a mathematical concept called dual number. So in this new way, you have x is equals to dual number, which is we'll define as a class later, right? Which stores the value and the value of x itself and also the gradient. So this is the trick, how we are translating the forward automatic differentiation in Python. Okay. So let me, if you numbers. So if you Google dual numbers, you'll reach a Wikipedia page. So in algebra, right? You have a hypercomplex number system. This is the expression a plus b of a plus b epsilon, right? So you have a dual number system. So this is a concept taken from here, from algebra, not from the Wikipedia. It's from algebra, right? So we'll be looking at that shortly, right? Now for the problem, I talk about this just now, that for every variable that we wish to compute, we need to run the program all over again, right? Again, if we have 1,000 variables of x, and you just want to compute the derivatives of, or the partial derivatives of z with respect to x, right? Then you have to do 1,000, and you want to compute for 1,000 variables, you have to do 1,000 computation of the same program. So this is computationally inefficient. And because of that, because of this is just say, this is inefficient, right? Because if you have 1,000 variables, then you have to keep setting one and zeros and ones 1,000 times. So that's why we're going to do reverse mode automatic differentiation. But before we go to the reverse mode automatic differentiation, I plan that we do the forward mode automatic differentiation. Let's do this first. Okay, let's do this first. So we'll do a class. We'll define a class, dual numbers. I haven't uploaded this yet. Yeah, I haven't uploaded this yet. You can follow along, or wait until I define the class. I'll define the class first, right? And then I'll upload. Then maybe you can follow along. Okay. So just a moment here. So we want to define x as a dual number. Yeah? So we'll use a class. We'll name the class as dual number, and we'll define with self some value, d value. So d value is your derivatives. So this is where we store your own value and the derivatives of the value. So we want to do this, right? X is equals self value, and the derivatives value of self value. This is what we want to do in dual number, right? Because you just want to have one variable or one class that stores both both values. So you have self value equals value, and then you have self d value equals d value. So this is your derivative. Okay. I'm just gonna have define some string function here so that can automatically, yeah, this needs space it here. Okay. Now So I upload this. Just a moment, yeah. So I've uploaded this into the GitHub, right? Because you need this symbol, I guess, right? The epsilon, right? And we'll go through the examples, yeah. We'll go to well, not examples. I mean, we'll go through the exercise, yeah. And then maybe afterwards, after we written some more, we've progressed some more, we're gonna, I'm gonna upload the file some more. Okay. Now, you have, for example, yeah, we can do multiplication. Right. I'm just gonna save time and right. Just test this. So here, for example, I've added this multiplication operation here. So what this does is it takes itself, so it's multiplication and some other values, right? And it does this operation. How do we define this? By here. So returning the same class. And this line, what is this? This is just x times y. Okay. And this line is this expression over here is this. So I'm just going to give you maybe 2 minutes, right? For you to have a look. For those who haven't, kind of haven't seen it, haven't, get it yet. What does this operation or functions does, right? So you have here, when you have multiplications, right? You are doing the multiplication here, and you are doing the derivatives whenever you have multiplications or product rule here. So this is self value times other times d value plus other value plus times self dot d value is actually a translation of this. Okay. Now, if we, so far no problem. And if we can retest it here. So therefore, you can, if when you have defined your class dual number class here, then you can, you can do this. You can have x, which the self value is 1 and its derivative is 0.5, for example, yeah. Y equals whole number. This is, for example, this is some, arbitrary values that I'm putting in here. Please don't think too much of why is it 1, why is it 2, why is it 0.5, why is it 0.7, right? Let's keep that in view. You'll see this at the end of the whole process, right? Hopefully. So we have this. Why am I?
I think because there's no underscore in the init.
This one. Thank you very much for that. Yep, thank you very much for that. Okay. So, and then you have z equals x, some y multiplied by y. So z is automatically a dual number itself, right? Z is automatically a dual number itself. So you have print z, right? So if you print, I just can do x and just love it. So this is just for view, for readability, I'll just do this. So this is right. So as you can see, we have defined our dual number 1 and 0.5, and we have defined the variable y as dual number. We have given some. This is the value of y, and this is dy. This is dy. This is dy. 0.7 is dy, right? So you're writing the expression. So this part of the expression is derivatives, and so you have another. You do some operation on these two dual numbers, and you have this. Why is this possible? Because we have already defined this multiplication or the product, or using the product rule. Okay. Do you have any questions? So I'm not going to. Sorry.
So far, no.
Okay, so far okay. So far fine, yeah. Because not many deep learning courses out there will talk about this, right? If you go on Coursera, I don't know about Coursera, Andrew Ng. I'm not sure about that. We go to Udemy, Stanford. Maybe if you go to some deeper deep learning courses, you will find it, right? But those, because most of the deep learning courses you'll find on YouTube or on the net will talk about how to implement deep learning models, right? What I'm trying to do here is I'm trying to give you understanding why is it working. I mean, how does it work? How does it really work? So when you go into you have a job and you can talk about forward automatic differentiation with your colleague, and kind of maybe they'll be impressed. I don't know, right? And it helps in your career. Okay, so this is the idea. Now that we've formalized the rules for multiplication, right? We can do the same for the rest of the operations. For the divisions, we have to use the true divisions, not the floor divisions, and the subtraction. And you can do for addition, right? Addition and subtraction, and maybe division is the it's kind of tricky, and also power. So we are here, as you can see, we are formalizing the differentiation rules. By defining the differentiation rules here, then we can compute, we can do this operation. And when we do this operation, x multiplied by y, it also computes the local gradient. Not local gradient, it also computes the gradient, because the local gradient is stored here. It's already stored here, right? This is the concept of dual numbers. Now, just to so I'm going to give you maybe 20 minutes for you to populate this. test addition, subtraction, division, and power. And then you can, play around. You can play around. You can test your dual number functions.
So that means for like division, we'll take the quotient.
Sorry, I can't. Tak berapa dengar, Alan. It's not very clear. Yeah.
So if we take, for example, division, we'll apply the quotient rule on the for the division.
Yes. It's good. So you have to basically you are translating this, right? All this, what is it? Into here. So you're returning the number. For exponential, it's a bit tricky. Yeah. For exponential or the power rule, it's a bit tricky. But you can do for addition, subtraction, and division. So have a go, 20 minutes or half an hour, I don't know, right? And you can also test your own dual number function. So you can do lah, for example, z equals, once you define your, the differentiation rules, right? When you have formalized it, you can do x plus y, right? If you haven't done this obviously we incur error, right? So you can do z equals x divided by y and so forth. I'm going to stop here. I'm going to pause and give you 20 minutes to do this. The idea was like, okay, so maybe you'll see, if for our tutorial or our lab, we have labs on Mondays, right? So as you can see, the course is structured to be like 2 hours of lectures and 1 hour of tutorial, right? But I found, for example, in the case for this topic, the automatic differentiation, it is better for me to do a 1 hour lecture and 1 hour or half an hour, 40 minutes of tutorial. So this is kind of a tutorial, right? Because you're doing in class exercise. So don't, I hope you are not surprised. So sometimes during class, I'll do a bit of tutorial because it just makes sense to do that. And sometimes during tutorial, I'll do class because it also makes sense to do that. Okay, so I'll give you 20 minutes. You can do addition, subtraction, division, and power, and test your dual number functions. See whether you can, your dual number functions are correct or not. It's kind of straightforward at this point. If you already got it, right? It can be like, when you first see this, the concept of dual numbers and the concept of defining the differentiation rules, it can be a bit of confusing. But once you got it, you know that you can feel that it is quite simple. But have a go anyway. So I'll be back in 20 minutes. Yeah. If you have any questions, please ask me. while you're you know, testing your dual number functions, you might also want to, you know, define the trigo functions. Yeah. Let me just Okay, so I've added some more. Just 1 minute. This is because I don't have the operations here. Should be fine. Yep, it's really fine. Okay. So hopefully you're okay with the dual number, right? You are able to do to define the addition operation, the subtraction, the division, and the power. The power is a bit tricky, right? We only have 10 minutes left. I'll probably do this during the tutorial. We'll revisit this during the tutorial as well. So you can test your dual numbers, right? Here I've only tested for multiplications, right? Or the product rule, right? There is only test for the product rule, the multiplications. But in a sense, we want to test for the one that we did in the slides. This guy, right? We want to test for this. Yep, we want to test for this. X is equal to y, b equals sine of x, a equals x times y, z equals a plus b, and you want to find the derivatives, right? Now, in order to do that, right, because if we look at this, we have sine of x here, right? So you have to define your multiplications and the addition functions. And also you have to have a sine of x over here, right? You have to have a sine of x over here. So that's why I've, implemented the sine of x over here. So this just returns the sine of x, as this is derivatives of, so you differentiate sine of x, you'll get cosine of x times x dx dt, right? That's what it means here, right? So your task, right, is to implement the cosine, tangent, exponential functions, right? And of course, you can verify it yourself, right? You can verify it, giving it some values, and you see if it calculates if it's okay or not. Now, this is what our objective is. We've talked about z. This is the z equals x times y plus we want to do this, right? Given x is 0.5 and y is 4.2. So in order to do this, you only need to define the multiplication, the addition, and also the sign. Sign is given here. Yeah. Trigonal functions is given here. Sine of x is given here. So you have to only define the addition and the multiplication in your dual number class, which is pretty easy. Okay. So if we do this, what do we get is x is 0.5 and y equals 4.2. Calculate it using by hand, verify by hand. If x 0.5 and y 4.2, what does this function gives you, right? And what is dz over dx and dz over dy gives you? You want to do that as well. So sorry, my mistake. We're not going to do this. We're going to do a simpler one. Right, a simpler one. So we have x and y and z, and you want to see whether in this case your function can take your dual numbers can be in the form of a sine function. Yeah. And what you want the answer for what is z, what is dz over dx, and what is dz over dy. Not over, what is dz of dy. What you wanna calculate. And you can do this by hand, right? You can do this by hand. You can differentiate this and do this by hand. Any questions? Never mind. We'll revisit this during the tutorial. Would that be okay? Would you like that? Yeah. Or you find okay, it's okay lah, doctor. This is quite straightforward. It's quite simple. Yeah. We're fine with this, right? We can also test it ourselves.
But how do you apply this on our current form of low number, or is that something?
Sorry, it's not very clear.
How do you apply the trigonometry functions like sin and cos on our current form of dual number?
The dual number.
Or is it something?
I don't know if it's your mic or something. Your voice isn't very clear. I can hear the word dual number. How you apply dual number? Okay, it's better now. Yeah.
Can you hear me now?
Yeah, it's much better now. Thank you.
How do you apply the trigo functions like sin and cos on our current form of dual number, or is it something we should figure out?
So we define it here, right? We define it here. So here this is actually from the differentiation rules. This is the same thing. But we're not defining it. We're just returning as a dual number, right? But we're not defining in this class. We're not doing def for sine of x or something, right? We're not doing that. So here is the sine of x value, straightforward, and this is the derivatives. But you need to implement this lah. But this is this implementation is just for for you to check yourself. You have to look at the rules. So for the Trigo rules, it should be some it's a bit small here. So cosine of x equals to minus of sine of x, right? The derivatives of cosine of x with respect to x is minus sine of x. So just a moment here. So you have to just this will be returning cosine of x here, and then negative math dots negative 1 times math dot sine of x values. So when you have this function, this Trigo function, you're putting in why can you do this? Because x is a dual number, right? This x is a dual number. Why is it x is a dual number? Because you can do x dot value, right? If x is something, right? If x is just a normal variable, right? Then you can't return a dual number, right? Because x is defined as a dual number, right? X is if you do x1, then you can't do you can do x dot value, right? Because you are not defining what is x dot value is, which is self dot value lah, right? So in this case, x itself is a dual number, and because of that, you are returning a dual number. Did that answers your questions? So I'll be looking forward. Maybe you already solve for this. What is C? What is dz of dx? What is dz of dy? Z is of course is a dual number, yeah. So I've also uploaded this on GitHub. Yep, have a class of dual number of the multiplication. You can test your dual number functions. You can implement the other math functions here, right? Your cosine, tangent, exponential, right? And this is putting in all together. Even though you haven't done cosine, tangent, exponential, it's fine as long as you have the sine and you have the multiplication and the addition. That is all what you need, right? You only need that. You don't need subtraction, division, power, because I think so. Yeah, because we're doing here. We're only doing a multiplication and addition and the sine function. All right then. So if you have any questions, do ask me. If it's not, it's already 4 o'clock. I'll just officially end the class for today. Thank you very much. Hope you know have an understanding of how forward mode automatic differentiation is being applied in Python or in coding, to be exact.
Thank you, Rada.
Okay. So if there are no questions, that's all for today, right? You can ask me some questions. Probably we will revisit this during tutorial, yeah. We'll see.
Doctor,
Yeah, sure.
sorry, I have a question. So about the for if we do the power function, right? For the dual number. So do we need to have a constant another argument in the
So the dual function is a bit tricky.
yeah, this one I can wrap my
Right.
head around it.
Yes, the dual function is a bit tricky. I'll give you a hint, right? I'll give you a hint.
Okay.
My implementation also is not perfect, right? My implementation of the power function is also not perfect, but the because you are basically, in power function you're applying a power function as well, right? So you
Okay.
kind of like overriding these methods, right? But in the methods that you're overriding, you're using those same methods, right? So it kind of it's kind of confusing. So one way, it's not a perfect implementation, is for you to have a for loop. So basically,
Okay, I see.
you see, you're doing, because in power function you have to use the power function, which is see, right? So in order to avoid what is a power function, is also is a multiplication lah, kan? So
Yep.
it is your own self. So you're avoiding the power functions, right? So you have to use the for loop to do the multiplication.
All right.
Okay, that's the hint.
Okay, I'll try.
Yeah, it's
Okay,
not even
thank you,
perfect.
doctor.
It's not perfect, but
Okay.
that's one way.
All right, thank you so much.
Right. All right then. If you have any questions, yeah, I'll be around for about 5 minutes, I guess. If you have no questions, that's all for today. Hopefully, this class helps you. Yeah, no questions. That's all for today. Yeah, thank you very much.
Thank you, Doctor.
Thank you, Doctor.
Welcome.
Yeah, thank you, doctor.
Welcome.
Thank you, Doctor.
Welcome.